So what we're going to do now is we're going to start talking about motion in space. And in particular, we're going to be talking about the very basic physics of motion in space when we're starting to look at three-dimensional figures, right? Okay, or even two-dimensionally, we can actually utilize this in order to think two-dimensionally as well. So we want to start thinking to ourselves, we have a vector. We have a vector r, okay? And that vector, we're going to think of that as a position vector. So it's going to tell us a location in space. Yes, it's going to give us a vector, but if you imagine that the point that the vector points to, that's going to be our position in space. And so we'll think about that as a position vector, okay? And what we can do then is, because we have a position vector, if you think about that from that perspective, if we take the first derivative of the position, what do we get? We get velocity, okay? So the first derivative of position is going to be velocity. We've learned that before, and that's going to be the same thing now, okay? We're going to say, okay, well, if you want to know the velocity of the vector, it's going to be the derivative of its position. Now, something to get about that is that when we talk about the velocity of a vector, okay, remember it itself is going to be a vector. You take the derivative of a vector, you get a vector, okay, and so it's going to have a position and it's going to have a magnitude, or excuse me, a direction and a magnitude. So now, because we're thinking in three-dimensional space, right, or even if we were really like thinking in two-dimensional space, we've got to think that it's going to be moving in a particular direction and it's going to have a speed, and we'll talk about that in just a second. And that speed is going to be the magnitude, and then the direction tells us where is it moving towards, okay? Now, if I take the derivative of velocity, remember that's going to be acceleration, okay? So we could see there that acceleration, a of t, which is also a vector, okay, is going to be the derivative of the velocity vector, which is the second derivative of the position vector. Exactly the same as what you would be doing if you were looking in single variable calculus or, non-vector variable calculus. All right, so there that is. And that also is going to have a direction, and it will also have a magnitude. Okay? What we want to do, though, is we really want to differentiate now between what we call velocity and what's called speed. In two dimensions, we oftentimes think of velocity and speed as being kind of the same thing, and actually they aren't. Okay, what speed is technically from a physics perspective is it's actually the magnitude of velocity. Okay, so speed is going to be the magnitude of velocity. So it's only part of the equation for our velocity vector. Okay, so our velocity vector, it's got a direction and a magnitude, and the magnitude of that velocity vector is called speed. All right, you can kind of think about that if you're thinking about forces, right? Remember that you've got the strength of the force and the direction that the force is being applied in. All right, we talked about that before. It's kind of the same idea here. When it comes to velocity, we're going to have a direction, we're going to have a magnitude. All right, and so that's how we find these things. We start out with our vector valued function. If we want to know the velocity of the particle that's moving along the vector valued function, we're going to take its derivative. And if we want to know the acceleration, we're going to take the derivative of that velocity, which is just the second derivative of position. All right? We've seen all of these relationships before. So let's say, for example, we have this vector valued function, r of t equals t squared I plus 5 minus t squared and square root j. So what we'll need to do in order to find the acceleration, the velocity, and the speed, we'll first find the velocity, v of t, and that's going to end up equaling the derivative of r of t, which is going to be then 2ti plus, and then we'll get negative 2t times 5 minus t squared to the negative 1/2 times 1/2 j. And so just simplifying that, we get 2ti minus t times 5 minus t squared to the negative 1/2 j. If we want to know the particular velocity at a particular point, all we've got to do is we've just got to plug in our t's, right? We figure out whatever t is, or say, hey, find it at 3 seconds or 5 seconds, okay? And we can go in and we can figure out what that velocity is. So at time t equals 1, what we do is we'd say that, well, we've got not v prime of t, but v of t equals 2 times 1i minus 1 times 5 minus 1 squared to the negative 1/2 j, okay, which is going to equal 2i, and then this is going to be negative 1, and this will be 4, so it's the square root of 4, so minus 1/2 j, and that is actually our velocity vector at time t equals 1. Now we'll find the acceleration vector, a of t. So a of t will end up equaling the derivative of v of t, okay, v prime of t, and that's going to end up equaling 2i, and then we'll find the derivative here using our product rule. So plus, this will be negative 5 minus t squared to the negative 1/2, minus 1/2 t times 5 minus t squared times 2t, or excuse me, times negative 2t. And all of that j. Simplifying that, we'll end up with 2i plus, we'll end up with, well, we'll actually change this to a minus, and so we'll pull out a 5 minus t squared, so it's going to be 5 minus t squared to the, well, by the way, this is to the negative 3/2. It's going to be 5 minus t squared to the negative 1/2 times, okay, this will be 1 minus, and then this will be then, or 1 plus, excuse me, t squared over 5 minus t squared, and that's all that, okay, j. By the way, for those of you who are wondering, like, how did he end up with t squared over 5 minus t squared? What I did was I factored out a negative 1/2 out of both, or 5 minus t squared to the negative 1/2 out of both figures, okay? And what that ended up giving me then is that ended up giving me, on the one hand, this becomes a 1, and then on the other hand, this over here becomes negative 1, okay? Because you pull out negative 1/2, that subtract, or that adds negative 1/2, and that becomes then to the negative 1. I should actually change that this thing here actually should be a minus, right? Because we pulled out the negative here. So this ends up being a minus. So we end up with, this is going to be 1 minus t squared over 5 minus t squared j. Okay, take a second to actually go through and do the algebra there. And so at t equals 1, that acceleration is going to end up being 2i, and then minus, okay, so this is going to end up being 4 to the negative 1/2, so that's going to be 1/2 times, this is going to be 1 minus 1 over 4, so that's going to be 1/2 times 3/4 j, which equals 2i minus 3/8 j, and that's our acceleration. Okay? Now let's go find the speed. So we're going to take the magnitude, so our speed, okay, is going to be the magnitude of v of t, and so that's going to end up equaling the square root of 2t squared plus, and this is going to be t times 5 minus t squared to the negative 1/2, all that squared. And when we do a little simplification, this is going to end up being the square root of 4t squared plus, and this will be then just t squared over 5 minus t squared. Okay? And for the moment, we'll just keep it at that. At t equals 1, what's our speed going to be? So our magnitude of v of t, that speed, is going to equal the square root of, and this will be 4 plus 1 over 4, which equals 17, the square root of 17 over 4. And that's the speed at time equals 1. Okay? And so basically that's how we find our velocity, our acceleration, and our speed vectors. All right? Velocity is the derivative of the position. Acceleration is the position, derivative of velocity. And our speed is the magnitude of our velocity vector. Now that we've got some math under our belts, let's actually talk about understanding acceleration and velocity from, say, for example, a physical perspective. Let's suppose that you're on a curve, you're on a road, okay? And here you are, here's your car. Your car is moving in it's kind of pulling a right-hand turn, okay? And so because it's pulling a right-hand turn, the velocity of your car, okay, is moving, right? You are moving in this direction, okay? That's the vector, and that's your velocity vector. That's v, okay? So there's v, there's your velocity vector. Now, here's the thing. Acceleration has two components, right? It changes direction, and it'll change speed, or it'll change velocity, okay? So, or change the speed, excuse me. So, like, basically, what you think about when you think about, like, acceleration is a change in velocity because it's the derivative of velocity. But your velocity can change in that the velocity can either change direction or it can change speed. You can actually decelerate, you can accelerate, you can get faster, you can get slower, and you can actually change direction. So what we do is we kind of conceptualize, like if you're moving into the turn, your acceleration is going to move you into that turn, okay? So like you're going to accelerate into the turn, all right? And so we imagine that we have like a vector, and this is our acceleration vector, and it's moving into that turn as you move the car around, okay? And that's kind of envisioning what's happening to your acceleration vector, okay? And so we want to think about that and we say, okay, all right, well, so that the acceleration is moving that way. Well, why is it that as I'm moving into and I'm making a right-hand turn, I feel the pressure or the force as I'm moving left? And the reason why that's the case is because your body, okay, is moving, is compensating for the force going into the turn by moving, like pushing away from that acceleration vector. Okay, and so that's why we actually feel that, right? Okay, we feel like a compensation force against the acceleration as it moves into that direction. Now, if you think about it, the acceleration, it changes direction, it changes speed, and so what that means is that it has two components. So it has two components. On the one hand, if we have, here's our position, all right? So here's our position vector, it's r of t, and r of t kind of like defines our position. On the one hand, our velocity, that's the tangent vector, right? Because if you think about it, the derivative of r of t, that's going to be a tangent vector. So you imagine, oh, okay, that's the direction of t of t. Okay, we imagine, all right, there's t of t. And then also, in addition to that, we've also got, right, we've got a normal vector. Okay, so we've got this normal, and that's n of t, and that's going to be in the position perpendicular to our tangent vector. Okay, that's the direction of the normal. If you look here, let's say, for example, what we've got here is that our our acceleration, okay, so I'm going to extend out my normal vector just a little bit. Our acceleration vector is going to have a part that is, right, if you kind of think about it, it's going to be in the direction of the tangent. Let me redraw that. Okay. And so, and it's going to have a portion that's going to be in the direction of the normal. Okay. So we have a portion of the acceleration vector, or a component of the acceleration vector, right, a of t, that's in the direction of the normal. Excuse me, in the direction of the tangent. Right, in the direction of t of t. And then we have an, which is in the direction of the normal vector. And if you can envision, right, you can imagine that we've got this vector here. We've got our acceleration vector, which is theta away from the velocity vector. Okay, so that's theta right there. And if you think about that, what that means is a little bit of geometry. That means that this thing right here is also theta. All right. And we form a triangle. Okay. We form a triangle with the normal vector and the tangent vector being the horizontal component and the vertical component of this acceleration vector. Okay. So that's kind of the deal there. So if we kind of think about this, I want to think about it in terms of in some terms of things that we've worked with before. Our velocity vector v of t is in the same direction as the tangent vector. The difference between t of t and v of t is that t of t is divided by the magnitude of r prime of t, right? T of t is unit. That is it's a length of 1. All right. Then we have our normal vector, which is perpendicular to t of t. So n of t, right, is orthogonal, and that's that picture. It's orthogonal to t of t, and which also means that it's also orthogonal to v of t, right? Because v of t is in the direction of t of t. Those are in the same direction, okay? Then we can split up our acceleration vector, because our acceleration vector is moving in a particular direction. We can split it up into our a of t, which is the direction of the tangent, and an, which is actually in the direction of the normal. And we're going to look at how it is that we're actually going to go out and do that. So we're going to use this information in order to actually generate kind of an understanding of what we would call the plane of the acceleration vector, or a component form of acceleration. That is, breaking it up into that tangent portion and that normal portion. So one thing that I want to get is if I write just v of t, okay, v of t without a vector, that's going to end up being, that's going to equal the magnitude of v of t, okay, and that represents speed. So I want to just be very clear that when I write without the vector, that v of t is going to end up being my speed component, okay? So what we'll do now is we'll start out and we'll say, okay, I've got v of t, and v of t is just r prime of t, right? Okay, and we also know that the tangent vector, t of t, is going to end up being r prime of t times the magnitude of r prime of t, okay? So consequently, if I rewrite this, r prime of t, so v of t, right, which is r prime of t, is just going to end up equaling, right, we'll multiply t of t times r prime of t, okay? So it'll end up being r prime of t, magnitude times t of t, which is just equal to, remember that this is going to be, r prime of t is just v of t, which is going to end up being our speed, times the tangential portion, or times the tangent vector, okay? So our velocity vector is going to be the speed times the tangent vector. This makes total sense if you think about it. Remember that speed is the magnitude of acceleration, and the tangent vector is the direction of the velocity, right? Okay, because it's simply just, it's a unit vector, right? It's a vector with length 1. We made it unit. And in addition to that, what we have is, so if we take it and we multiply it by the speed, we multiply the magnitude times the direction of the velocity vector, you're going to get the velocity vector. It kind of makes a lot of sense if you kind of sit down and think about it for a second and what all these mean. Okay, so we've got that. So we know that v of t, right, is going to equal v of t, the velocity vector, times t of t. Okay? Now to find acceleration, a of t, right, is going to equal the derivative of v prime of t, or v prime of t, which equals, and so that's going to be the speed vector prime times the tangent vector, t of t, plus, and this will end up being v of t, the speed, times t prime of t. Okay? Right? And that's just simply, that's just the product rule. So what we need now actually is we need that t prime of t. Well, remember that the normal vector, so recall, the normal vector n of t is going to be equal to t prime of t divided by the magnitude of t prime of t. Okay? And so, if we think about this, well, what does that mean, right? Okay, the magnitude of t prime of t. That means that if we take, here's t prime of t, it'll end up equaling the magnitude of t prime of t times that normal vector, n of t. So this then gives me, right, if I just go substitute in for t prime of t, I'm going to get that a of t equals v prime of t, or excuse me, equals v prime of t, that's the direct derivative of the speed vector, times the tangent vector, t of t, not a vector, pardon me, just the speed equation, plus v of t times the magnitude of t of t, times the normal vector, n of t. Okay? Speed, direct derivative of speed, speed prime, just to be careful so we really are clear on that. Now we'll recall, we got another thing from last lecture. Recall that what we know is, in addition, that my curvature, K, is going to equal the magnitude of t divided by the magnitude of r prime of t. And so that ends up giving me K, that implies that K times the magnitude of r prime of t is going to equal t, the magnitude of t prime of t. Okay? And now what I can do is I can actually substitute this in as well. So I get now that a of t equals v prime of t, the speed, times the direction of the tangent vector plus, okay, we've got v of t times k times, and then the magnitude of r prime of t is v of t. Okay, that's what it is, right? We actually figured that out. This is v, the velocity vector magnitude. Okay, so that's simply just the speed vector again, times the normal vector, n of t. And so what we get now is we get that our acceleration vector is going to be v prime of t, okay, the derivative of the speed vector in the tangential direction, plus the speed vector squared times the curvature, okay, times the normal vector. So what we have here now, right, as we're working, we see that this is the tangential portion, because it's in the direction of the tangent, and this one here is going to be the normal portion. Okay? Now, let's remember a couple of things, right? Remember that t of t, or the magnitude of t of t equals 1, and the magnitude of n of t also equals 1. Right? So both of those end up equaling 1. So that means that in the direction of the tangent, this is, in fact, that magnitude of the vector is going to be v prime of t, and in the direction of the normal, this is the magnitude in the direction of the normal. So if you imagine, we'll go back and we'll draw the picture again. Okay? So we'll draw this picture again. And so we've got our acceleration vector. Say the acceleration vector is moving now in this direction, just to make the diagram look good. And so here, and here's the curve. Okay, so here's the curve. Oh. Here's the curve. Okay, and so we've got, oh, it's going to be kind of moving in that direction. So here's normal to the curve. Here's tangent to the curve. Okay, so we've got a triangle, a right triangle here, and we've got AT, the tangential component of the vector, and that'll end up equaling, okay, v prime of t dotted with t of t, or not dotted with, but times t of t. And then here's an, which is our normal component, or the normal portion, and that's going to be v of t squared times the curvature times, and this is times, n of t. Not dotted with, but times n of t. Okay? And there we go. Okay? So here we have tangential component of the acceleration, and here we have the normal component of the acceleration. And those are our two components, and that's how we actually end up with the formulas that we got for them. I have to make a little correction here. This actually should be v prime of t. It's been v prime of t every single time. It continues to be v prime of t. That is the that turns out that's the derivative of the speed vector, right? Which is in many ways is just the magnitude of your acceleration. Let's take a look now, and we're going to create some alternative formulas for a sub t and a sub n, and these are going to be like the magnitudes of the components. All right. Notice that they don't have the vector symbol over themselves. Okay, so they're not like a of t themselves. So like for example, when we had this a sub t, it's going to end up being, on the one hand, we wrote it before, and it was going to be v prime of t. Made sense. And then we had also a sub n, okay, the portion in the direction of the normal vector, and that ended up equaling v of t squared times k. Okay, and we saw those before as well. Okay, and those are those magnitudes, one in the direction of the tangent vector and the other one in the direction of the normal vector. So now I'm going to draw my acceleration vector again. Okay, and then I have, on the one hand, I've got something that's moving, right, in the direction of the tangent vector, t of t. Remember that? And so t of t here is running parallel, and right here, this is theta. That's the angle between a and t. Okay? So the magnitude of this line right here, okay, the magnitude of that line, right, is going to be the magnitude of a times cosine theta. Okay? Standard, right? It's the cosine theta part because this is also theta, right? If you kind of remember your geometry, right? Those are internal vectors. They're being cut by a transversal. Two parallel lines cut by a transversal, and those are internal angles. So there's your theta, so it's going to be a cosine theta. Okay? Now, in addition, if I switch this, okay, and I make this now theta, all right, so I make this theta, and that's if we're working with the normal vector, okay, then this length right here is also a cosine theta, okay? But with regard to, we'll call it cosine theta 2, a different theta, all right? Now, what we're going to get here is that I want you to notice that if I take magnitude of A and I multiply it by the magnitude of T, cosine theta, that's actually equal to, these two things are equal, okay? They're equal, and the reason why they're equal is because the magnitude of the tangent vector is equal to 1. Same thing is going to be true of the normal vector. And this thing here is a dot t. So the magnitude of our component, at, is actually going to be just a dot t. If we go down here, okay, and now we utilize theta 2 as the angle between a and n of t, what we get is as well, we get that this, a cosine theta 2, is also going to be equal to a times the magnitude of the normal vector times cosine theta 2, okay, which is also just a dot n. So what that means is that the magnitude of the normal component is going to actually be a sub n, and that's going to equal a dot n. Okay, and that's another way that we can actually figure out the magnitude of at and the magnitude of an. And this is actually going to be a lot easier. What I'll do now is I'll just give you some alternative formulas in addition to these two. There's at, there's an. Okay, and here we go. So now what we're going to do is we're going to look at these equations. So we've got that magnitude, a of t, is equal to a dot t. Okay, and that's equal to v dot a divided by the magnitude of v. All right, you can actually see that we've done this one before. And then a sub n is going to be a dot n, and that's going to be the magnitude of v cross a divided by the magnitude of v. And then we have another alternative one, which is the magnitude of a squared minus the tangential magnitude squared. Okay? And then what we end up with is we end up with this formula right here. Okay? And the reason why that this is the plane, or defined by a plane, is because we have two vectors. We got t of t and we got n of t. Okay? And they're going to be perpendicular to each other. And so what we've done is we've written a of t. A of t, that vector, is a linear combination So it's a linear combination of t of t and n of t. Okay? So these two, they form a plane, n of t and t of t. And what we've done is we've located a of t on that plane. Right? We've got, remember you'd have to have two vectors because you need to create a normal vector. All right? You take the cross product of t and n of t, you get like that binormal vector. That actually represents, like, it helps us give this the direction of the plane, right? And then we have a, locate any point. And so these two vectors, they end up defining for us a plane, and we can locate our acceleration vector on that plane. Okay, and there's a name for it, it's the oscillating plane. Okay? All right, so let's suppose that we have an object and it moves in a path defined by the vector valued function r of t equals 4ti plus t squared j. And we want to find a sub t and a of n as functions of t. So this is just, notice no vectors on there. Well, all we're doing is we're actually defining them as the tangential component, or that magnitude, and the normal component. And then we're going to find a sub t and a sub n at time t equals 7. All right, so we'll start out, and what we need is we need a of t, okay? And we're going to let a of t, we're actually going to define this one then as v dotted with a, okay, divided by the magnitude of v, okay? And the reason why we'll do that, that's actually probably just the easiest way to go about this. So we start out, we know that r of t is 4ti plus t squared j. So r prime of t is going to equal 4 comma 2t. And our double prime of t then is going to equal 0 comma 2. Right? The magnitude of v then, okay, or a speed, is then going to be the square root of 4 squared plus 2t squared, which equals, and that's going to be 16 plus 4t squared, which is 2 times the square root of 4 plus t squared. Okay, so our tangential component, a sub t, is going to end up equaling, and it'll be, well, first we've got to take that dot product before we do anything. There's our magnitude. Take the dot product. So v dot a is going to equal the dot product of 4 comma 2t dotted with 0, 2, which equals 0 plus 4t, which just equals 4t. Okay? So a sub t is going to equal 4t over 2 times the square root of 4 plus t squared. And thus, that's going to end up equaling 2t over the square root of 4 plus t squared. Excellent. To find our normal component vector, now that I've actually got a sub t, and I know a, my acceleration vector, which is just r double prime of t, that's a. Okay, by the way, that's a. Here's v. Okay. What I can do now is a sub n is going to end up equaling the square root of the magnitude of a, that vector squared, minus a sub t squared. Okay? And so we'll first find the magnitude of a. So the magnitude of a is going to equal, it's the magnitude of 0, 2. Okay? Which just equals the square root of 2 squared, which equals 2. Okay? So that's the magnitude of a. And we know a sub t squared, so our normal vector, this is going to give me the square root of, so 2 squared minus 2t over 4 plus t squared squared, which equals the square root of 4 times 4 plus t squared minus 4t squared divided by 4 plus t squared squared. And all I did there was I just used common denominator. And this actually should be 4 times 4 plus t squared. Okay, and this is actually the square root, excuse me. Square root, and that's not, so that's not squared, that's just regular. Okay, remember up here that it's over the square root of 4 plus t squared. I forgot my square root. So I just multiply by 4 plus t squared. So this gives me the square root of, and this will be 16 plus 4t squared minus 4t squared divided by 4 plus t squared. And so that ends up equaling, well, it's going to be 16 over, or square root of 16 over the square root of 4 plus t squared, which is 4 over the square root of 4 plus t squared. And there is your a sub n. Okay, and there we go. So our tangential component, a sub t, is going to end up equaling 2t over the square root of 4 plus t squared. And our normal component, a sub n, is equal to 4 over the square root of 4 plus t squared. All right, you just got to utilize those formulas. Once you've done that, you're good to go. Okay, and that basically is that. Now, let's go figure out what it is at a time t equals 7. So a sub t at 7 is going to equal 14 over the square root of, and this is going to be 53 because that's 49 plus 4. And a sub n is going to equal 4 over the square root of 53. There we go. And that gives us both our tangential and our normal component, part of the components, at time t equals 7. All right, so easiest formulas for us to use are probably for this tangential part is to use v dot a over the magnitude of v. And for a sub n, we'll use the magnitude of a squared minus a sub t squared. Okay? And there you go. First, figure out what a sub t is, because you're going to need it in the other formula. Okay? And you'll actually utilize the vectors v and a as well. All right? Cool. There it is. And this completes actually our lecture on velocity, acceleration, and speed.